Hey Global Impact, this is Mr. Ellinger. This lesson is on absolute value functions. Our learning target for the lesson, we want to be able to graph absolute value functions. Some essential understanding for you from this lesson. Just as the absolute value of x is its distance from 0 on a number line, the absolute value of f of x, or f of x inside our absolute value symbols, two vertical bars, gives the distance from the line y equals 0 for each value of f of x. The line y equals 0, also referred to as the x-axis. The simplest example of an absolute value function is f of x equals the absolute value of x. The values of a, b, and k in the form y equals a times the quantity, the absolute value of x minus h plus k, determine how the parent function y equals absolute value of x can be transformed. Making tables of ordered pairs can help you analyze the effects of the transformation on each coordinate. So as I said, just as the absolute value of x is its distance from 0, the absolute value of f of x gives the distance from the line y equals 0, again also known as the x-axis, for each value of f of x. The simplest example of an absolute value function is f of x equals absolute value of x. The graph of the absolute value of a linear function in two variables is a V-shaped and symmetric curve, call it a curve even though it's not curved, about a vertical line called the axis of symmetry. Such a graph has either a single maximum point or a single minimum point called the vertex. So here we have our V-shaped graph. Here is its vertex. There is a vertical line running through the vertex that we call the axis of symmetry. What that means is if I were to take my paper and fold the right side over on top of the left side about this axis of symmetry, this part of the graph would lay right on top of this part of the graph. That's what it means for the graph to be symmetric about that line. So here we have a table of values that was used to generate this, and then here is the actual function itself. Okay, so this is the definition. So this is the definition of an absolute value function. It's what's called a piecewise function, and we will explore that here in just a few minutes. Okay, so the family of absolute value functions, you can see in this box here what happens when we do different transformations to the parent function y equals the absolute value of x. We can vertically translate, we can vertically stretch or compress, we can horizontally translate, we can reflect. Okay, and these concepts are very similar, exactly the same actually to what we talked about in our last lesson. So what is the graph of the function y equals the absolute value of x plus 2? How is this graph different from the parent function? Well, y equals absolute value of x plus 2. We didn't change anything in here in the absolute value, so we know there's no horizontal translation. Basically what we did was we took the parent function y equals absolute value of x and we added 2 to the values. So this is a translation. So our parent function, we know, looks something like this. And I'm not using a straight edge, so this isn't going to be exact. There's our parent function, y equals absolute value of x. If I translate this up 2 units, I know my vertex is now going to be a 0, 2. So my function that I'm working with here looks something like this. There is y equals absolute value of x plus 2. And again, the red one was y equals absolute value of x. All right. The transformations of the form y equals absolute value of x plus k affect the axis of symmetry. Well, if I take a look here, when I translate vertically, the vertex stays right on that y-axis, right? Well, the axis of symmetry in both, since the vertex is still on the y-axis, is still going to be the y-axis here. So here's a question, a multiple choice type of question. Which of the following is the graph of y equals the absolute value of x plus 2 plus 3? Well, the plus 2 inside the absolute value tells us we're going to have a horizontal translation to the left of our parent function. The plus 3 means we're going to translate this up. Answer D gives us that graph. Okay? We have our parent function would be right in here. We've translated it left 2, and we've translated it up 3. What is the graph of the function y equals absolute value of x minus 2 plus 1? Well, our parent function, we know the vertex is at the origin, and what I think is easiest to do is just to go ahead and think about where does the vertex go? So our vertex in our parent function is here. We know the vertex is going to be translated to the right 2 units, so to here, but then up 1 unit. So here's the vertex of our new function that we're working with here. So we'll just go ahead and graph this. And again, I'm not being real precise right now, but I would probably want to get some other points of data on here and make sure that I get a good graph draw with a straight edge. Okay, so translate, move the vertex, and then base everything else off of that. The right branch of the graph of y equals x, the right branch of the graph y equals the absolute value of x has a slope of 1. The graph of y equals some value a times the absolute value of x, with a being greater than 0, is a stretch or compression of the graph y equals absolute value of x. Its right branch has a slope of a. The graph of y equals negative a times the absolute value of x is a reflection of y equals a times the absolute value of x in the x-axis, and its right branch has a slope of negative a. All right, now here is an example. You can see what happens when we take a value and multiply by the absolute value of x. What is the graph of y equals 1/2 times the absolute value of x? Well, this graph is a vertical compression of the graph of f of x equals absolute value of x by a factor of 1/2. So we want to graph the right branch and use symmetry to graph the left branch. So what we would do is we would say the vertex, make a table here real quick. The vertex is still 0, 0, correct? Here we have 0, 0. Here we have 1, 1/2, and here we have 2, 1. So if we draw the right branch out, as it says, we know that absolute value functions are symmetric. So if we wanted to plot some points, we could come over here. We could plot negative 1, 1/2. We could plot negative 2, 1, and so on, and draw our left branch. So here's the general form of an absolute value function. Y equals some value a times the absolute value of a quantity x minus h plus k. Stretch or compression factor is the absolute value of a. The vertex is located at hk. So h and k tell us where the vertex is. And we have to be a little bit careful here. There's always a subtraction sign in here. So if this says plus h, then we know that our x-coordinate of our vertex is going to be a negative value. If our function that we're working with says x minus some value, then it's going to be a positive x-coordinate here. The axis of symmetry is the line x equals h. Okay? And the reason is because x equals h is a vertical line. X-only equations are vertical. And the axis of symmetry must go through the vertex, so it makes sense that x equals h, which is the x-coordinate of our vertex, is the equation of the line of symmetry. So some questions to think about. The absolute value function is actually a piecewise defined function, which I mentioned a few moments ago. What does this mean? What this means is, when I look at the two pieces, one piece is x when x is greater than or equal to 0. One piece is negative x when x is less than 0. Just draw a quick graph here. This is actually defined in two pieces. X and negative x, if you look at those two pieces separate, those are both linear pieces. Depending on the value of x dictates which piece of the function are you using. If x is positive, then we're using this piece of the function. If x is negative, we're using this piece of the function. Okay, so if x is a negative value, like negative 2, then we evaluate the function for absolute value, we know that the values become positive, so that's where we get the positive 2 aspect, and that's where we get this, point here on the graph, right? So it's called a piecewise function. It's defined in two linear pieces. Depending on what x is, dictates which piece of the function you're using. All right, so we'll do a lot more with piecewise functions later, but it's nice to get an introduction to it now. Have a good day, folks.